The focus of this webinar again is precision in corrosion inhibitor selection testing for oil and gas applications, which is the first right step. This initiative was not started recently. It has a long history, and the person who really started the whole thing was Dr. Winston Reeve. And I don't think anybody needs introduction. Winston does not require any introduction. He has been in the field for the last 60 plus years. And personally, he was the person who brought me from India to work on this project in 1994. And Winston has written several books. He has been running the BAF pipeline workshop for the last 30 years. And with that, I would request Dr. Winston Reeve to say a few words and to bless this webinar series. Winston, the floor is yours, please.
Okay, well, thank you very much, Shankara. So this is quite an interesting chronology of events here, starting back in the early 1990s. So the global issues that we faced at that time, there were really three of them. Energy. So we all needed energy to heat our homes and run the factories that we have in Canada and around the world. We needed water, clean water to drink, as well as water for industrial purposes. And then the environment, clean air. So energy, water, and the environment were the three global issues that we were looking at. And, it's really interesting that today those issues are, I would say, even more important today than they were all those years ago when we set out on this work. But drilling down now to pipelines, we had three objectives. Firstly, ensuring public safety and environmental protection. Secondly, improving the reliability of pipelines. And thirdly, enhancing the economic position, the security of supply, and the deliverability of oil and gas. And we could summarize those three objectives in one: failure prevention. So when we looked at pipelines, specifically sour service pipelines, well, it was pretty well known that failures did occur. And failures occurred notwithstanding the use of inhibitors to manage corrosion. So we thought, well, how were those inhibitors being evaluated and selected for the sour service pipelines? And we thought, well, maybe if we could develop maybe better procedures for evaluating the inhibitors, we'd get fewer failures. So that's the way we started off our consortium, which was called the Development of Standardized Methodologies for Evaluation and Qualification of Inhibitors for Sour Service. It turned out to be quite a large project. There was field work carried out in Alberta at different sites there. And in fact, in that slide, there's a couple of pictures. On the right hand, the top one shows Shankara and Wenyu Zhang and me at one of the field sites in Alberta. And the lower picture shows the field setup that we were using to evaluate the inhibitor performance using as many different techniques that we could in the field. And that's Alabachu Demos, who was a scientist, and I believe he's still a scientist at CanMet at the Devon lab. We completed the project, and the results were actually. I mentioned that field experiments were done in Alberta at different sites. Also, lab experiments were done in the labs in Ottawa and out in Devon too. And then with the round robin testing, the industries that were involved in the consortium carried out tests as well. And eventually the ASTM standards were drafted and approved. And so the project did achieve the objectives of developing the standardized methodologies. So I'm really delighted to be a small part of this first webinar in a series that will focus on inhibitor selection. And I just can't overemphasize the importance of the area in ensuring the reliability of pipelines and to ensuring that the best possible inhibitors are selected. So with that, I'd like to congratulate Shankara on setting up this inhibitor series. And I hope you found this little journey down memory lane to be interesting, give some information on how it all started all those years ago. So thanks a lot. And I have to leave in a few minutes, but I hope you have the very best discussions possible on this very important topic. So thanks again, Shankara. Is Shankara there?
Thanks,
It looks
Winston.
like he
And
stepped away, I think. There he is.
no. Thank you, Winston. Really appreciate it. I know that you are very busy, and in spite of that, you made time to join our webinar series and to start and bless it. Thank you very much, Winston.
Okay. All right. Okay. So bye for now.
Okay. Thank you. As Winston pointed out, the whole journey started in 1993 at the Banff Pipeline Workshop that was held in Canada. At that time, a group of industry experts, as Winston pointed out, identified the need for standardization of corrosion inhibitor testing. With that, they also started a consortium that Winston led between 1994 and 1999 that is known as CANMET Corrosion Inhibitor Joint Industry Project. The photos that Winston talked about were taken during this period, during the JIP. Independent to the JIP, in 1990s, I believe, NACE at that time coordinated a round-robin test on wheel test and bubble test, and they published a technical report 1D196, which unfortunately has been withdrawn, and that talks about the repeatability and reproducibility of wheel test and bubble test. Once Winston completed his JIP in 1999, coincidentally, ASTM held a workshop. Russell Kane was the one who started it. And in that workshop, it was identified that we need to develop a series of standards for the high wall shear stress laboratory methodologies. The 1994 NACE focused on wheel test and bubble test, which at that time were considered as low shear stress tests. So ASTM focused on high wall shear stress test, which included rotating cage, rotating cylinder electrode, and jet impeachment. Between 2000 and 2012, a series of standards were published, among which was the 2000 G202 standard test method with precision statement on rotating cage. We'll talk more about the precision statement and the process of developing it. The G202 round-robin tests were participated by 10 laboratories from across the world. Some of the labs participants are present in this webinar. The last ASTM publication was G208, published in 2012. And then we led the industry to uptake the ASTM standards. And in 2019, exactly 20 years after the first workshop, we organized a workshop in Houston, and in which we identified that even though we have got lots of laboratory testing uh, standards that provides step-by-step procedure, the end product, that is what I will get if I follow these steps, that information was not available. So that started the current GIP on corrosion inhibitors. And this was actually being led by Trevor Place. Trevor couldn't join the webinar today. He will join the future webinar. Today he's scuba diving somewhere in the ocean. Independent of the GIP, ASTM also started a corrosion inhibitor course in 2023. Right now it is being offered as an online course. So that is a background to this GIP and to the webinar series. Whether somebody is interested in the GIP or not, as an industry, we should be aware of the importance of precision as the first right step in corrosion inhibitor selection testing. And the webinar series is focused to emphasize the importance of precision in lab testing. Why that is important? Corrosion can be controlled by 4 means. By selecting appropriate material, or by applying coatings followed by cathodic protection to control external corrosion, or by addition of corrosion inhibitors to control internal corrosion. This is well known for the last several decades. If you look at the evaluation of these techniques for materials, the evaluation or selection of material is required in several regulations as well as in several standards. If you are going to select a material for shower service, everybody follows MRO 175, AMP or NACE MRO 175 or ISO 1556. And the oversight committee provides training as to how to select appropriate material. And the selection criteria is very, very quantitative. We have got ASTM standards, AMP standards that talks about characteristics of materials. So that, for example, if you choose 1018, we know exactly what the characteristics of 1018 carbon steel. Similarly, for coatings, we have got regulations, especially in Canada, that requires companies to follow CSA standards. And there are some AMP as well as other courses being offered as to how to certify the coating inspector and applicator. In the lab testing, very specific requirements. If you are going to carry out a CD cathode disbandment test, the coating shall pass at less than 15 millimeters disbandment. If it is exceeding 15 millimeters, the coating is disqualified. Very, very quantitative criteria. And cathodic protection around the world, we follow AMP or NACE SP0169. And that gives a very, very quantitative criteria of 850 millivolts versus copper sulfate. It's a very quantitative criteria. On the other hand, if you look at the corrosion inhibitor evaluation, to my knowledge, there is no regulation that requires quantitative criteria. And all our evaluation are all very qualitative. There are some quantitative criteria within industry, within companies, but as an industry, we don't have quantitative criteria. That is the focus of this webinar series. So what are the motivations for establishing precision in inhibitor testing? In 1990s, when Winston started the first GIP, they understood that The continued qualitative evaluation using laboratory methodologies whose precision is unknown could eventually crack under scrutiny of external examination. This was the motivation to start the process in 1990s, and still we have not achieved that particular goal of establishing precision in all lab testing. We could wait until regulations are imposed, but that might have some unanticipated consequences. For example, if you recollect, to evaluate green inhibitors in North Sea, the regulators came up with some specifications. So we don't want to wait. So oil and gas companies, operators, owners, chemical suppliers, and other stakeholders, we are in a best position to lead the targeted development of quantitative consensus standards. So that is the motivation for this webinar as well as for the JAP. If you are going to evaluate corrosion inhibitors, what are the properties we need to evaluate? In the JAP, we call them as T's: transportability, efficiency, availability, and secondary inhibitor properties. Transportability describes how the inhibitor is carried from its point of application to the location at which it should function as inhibitor. In the slide that Nihal provided, if I inject the inhibitor in the oil phase, it has to go through the interface, through water phase, and reach the metal surface. That is what we call it as transportability. And to our knowledge, we don't have a good understanding or good appreciation of the transportability factor. Efficiency is a measure of the extent to which the inhibitor can reduce corrosion when compared to uninhibited condition. This is an over-researched, over-published information, efficiency. However, there is no quantitative standards. Availability is in logistics to ensure that the supply chain is in place to reliably supply corrosion inhibitor at the location of application. When we select inhibitor based on efficiency, it might work very well in one location or one condition. It may not work in another situation. That is because of the secondary inhibitor properties. NACE has put out a standard 31215. It talks about 18 different secondary corrosion inhibitor properties that can affect the inhibitor performance. So the secondary inhibitor properties are highly variable, and this property is a measure of whether the inhibitor will have desirable or undesirable effect. So we need to cross the T's, but in our webinar series, we are going to focus on methodologies, laboratory methodologies to evaluate efficiency as well as secondary inhibitor properties. Transportability and availability, we'll talk about it, but they are slightly outside the scope of our discussion. So how do we evaluate these properties? For which we follow industry standards. There are 3 categories of standards: standard guide, standard practice, and standard test method. For transportability and availability, there are no standards to my knowledge. For efficiency, we have got several standards, but only one standard is the standard test method, which is ASTM 202. And for secondary inhibitor properties, we don't have many standards that we can rely on. What are the definitions or classification of this T standards classification? Guide is a compendium of information or a series of options that does not recommend a specific course of action. Basically, that guide increases awareness of information or approaches in a given subject. In the case of corrosion inhibitors, we have got ASTM G170 or NACE 1D182. So guide is the first step. The next step is standard practice. Standard practice provides a definite set of instructions for performing one or more specific operations, but it does not produce a test result. It tells a step-by-step procedure, but it doesn't tell what will happen if I follow the step-by-step procedure. What is the end product? Example is ASTM G185. The ultimate goal of standardization is a standard test method, which is a definite procedure that produces a test result. In other words, if you follow a step-by-step procedure, this is what you should get it. That is a precision statement. The only standard that is available for inhibitor evaluation efficiency is ASTM G202. The standard test method requires three basic requirements. First, repeatability. Two, reproducibility. And based on repeatability and reproducibility, the precision statement. Repeatability is a measure of variation one person will get if he or she repeats the experiment and using the same apparatus, same condition, following the same procedure. One person, one procedure, one methodology, one lab testing procedure. Reproducibility is a measure of different persons or different laboratories carrying out the same test using similar apparatus, same condition, and following same procedure. What is the variation we get is the measure of reproducibility. And ASTM has a well-established inter-laboratory studies to define precision based on repeatability and reproducibility. And as of now, we have got only ASTM 202. These definitions are slightly different from AMP, but they very closely match with one another. The only difference is that ASTM requires the precision statement development. Why are we bothered about the precision? We all want to hit the bull's eye. If you are going to select inhibitor or evaluate inhibitor, we want to select the best product, very target, to hit the target. So as a consequence, the gun should be sharp. Let us review some of the current scenario. One of the very common methodology we use to evaluate corrosion inhibitor is rotating cylinder electrode. And ASTM has been coordinating a round-robin test for the last few years. Many of us are participating. Under the same condition, using the same material, 13 laboratories produce corrosion rates that vary from 23 to 2000. Very large variation. The second methodology is jet impeachment. Nihal Obeshegara did some repeatability, not reproducibility, but repeatability. Under the same condition, he had a variation of 150 to 1200 milliamps per year corrosion rate. And NACE, at that time, as I said, coordinated a round robin, that is 1D196. On wheel test, we had a variation of 2 to 86 mpy. For bubble test, 3 to 47 mpy. Again, the variations are a little larger. And ASTM did the round robin test inter-laboratory studies, and they had a variation of, under the same conditions, different laboratories, 10 laboratories, produced corrosion rate that varied from 18 to 28. That is plus or minus 5 mpy variation. So this establishment of precision is what that helps us to target good corrosion inhibitors in the selection process. But the question is, are these precision good enough for our inhibitor evaluation? Let us take a step back and see what are the benefits of establishing precision. Let us assume that we are going to select inhibitors for a particular application, and we ask the vendors to produce their best products. We identify them as A to J. We compare their corrosion rate with uninhibited condition. Let us assume that we are using rotating cage. The key point here is that when we say precision, what is the variability under the same condition? In the rotating cage, as per the previous slide, as per the ASTM 202, it has a precision of 5 mpy. So if you get the lab data, we can rank them from 1 to 21. The corrosion rate varies from 1 mpy to 21 mpy. If you have to rank them, we'll rank them according to the corrosion rate from 1 to 10. We end up selecting probably inhibitor A. This is one approach. Let us also put the cost estimate into the picture. This is a cost estimate per gallon of inhibitor. Now, if we can also input the precision 5 mpy, that means that inhibitor A to inhibitor E, they are within the precision of rotating cage laboratory methodology. What it means is that the performance of inhibitor A to E are almost same or within the precision statement. In other words, they all have the same level of inhibitor efficiency. So in that process, we could select inhibitor E, which has lower cost, which will have the same efficiency. So that is the basic benefit of establishing precision of laboratory methodologies. So to sum up this webinar 1, we need quantitative evaluation that matters a lot because the precision statement helps us to establish a uniform framework for comparing chemical performance across multiple suppliers. It provides a consistent, defensible, verifiable foundation for evaluating inhibitor performance. So we can define why we selected the inhibitor from different vendors. It also provides a defendable framework for monitoring inhibitor quality in ongoing field applications. We'll talk more about it. In some parts of the world, they don't do any inhibitor selection, but they do monitor the inhibitor performance during operation, and for which also this precision statement will help. The inhibitor evaluation happens in the field first, so for which we either use our own labs or we use third-party laboratories. The precision statement will also help to qualify third-party testing laboratories so that we qualify the laboratories before they qualify the inhibitors for our need. So that is the premises of the webinar 1. With that, I will also quickly go through what we are going to do in the phase 3 of the current JAP, which is industry best practices for evaluating efficacy of corrosion inhibitors used in the oil and gas industry. And several of the sponsors are available at this webinar. And this JAP is being led by Trevor Place from Enbridge. And he was the one who kind of superheaded the whole JAP, and he brought several sponsors together. And we are in a process of completing. In fact, we have completed phase 2, and we are embarking into phase 3. When we started the JAP in 2023, the ultimate objective was to develop standard test methods. However, upon reflection, Trevor established that we had to do the JAP in 3 phases. In phase 1, let us collect and summarize what are the existing best practices from owner-operators as well as chemical developer and suppliers. And that was the phase one. In that phase one, we identified 23 applications across the oil and gas industry in which corrosion inhibitors are being used. In phase one, we conducted 226 interviews. Many of you participated in the interview. Based on the information we collected, in phase two, we developed a guideline representing the current industry best practice for inhibitor testing. And we developed the guideline for each one of the 23 applications. In that process, we identified 8 laboratory methodologies that needs to be standardized so that our inhibitor evaluation and selection across the industry will be consistent and based on precision. That is a focus on phase 3, development of standard test methods for the most promising or popular methods identified in phase 2. Phase 3 is being started on December 2nd, but we are opening this webinar so that people become aware of what is the importance of precision. Oil and gas industry operates in diverse environment. For the purpose of inhibitor selection, the JAP classified the applications or operations into 23 categories. And for each one of the categories or applications, as Trevor points out, the inhibitor selection, application, and secondary inhibitor property considerations differ considerably. As a consequence, each one of the application should be considered as a separate entity. So that was one of the things we found from this discussion. And based on that one, we conducted the interviews. As I said, 226 interviews are conducted. Some we had lots of inputs. For example, production pipelines, 38 interviews were conducted. And some of the applications, we don't have sufficient data. We are still continuing the interview process. So based on the interviews, we, in phase 2, develop individual reports to talk about how to select, apply, monitor corrosion inhibitors in the 23 applications. First, we establish the boundary. We talk about what are the corrosion types, what are the corrosion control strategies, which may include corrosion inhibitors, biocides, scale inhibitors, and so on. How in that application, the need for corrosion inhibitor is established. What are the efficiency tests that are being done to evaluate the corrosion inhibitor? What are the standard conditions in which the efficiency test can be carried out? How the operators can evaluate inhibitor efficiency for their operating conditions, what factors they need to consider for a given application, what are the different secondary inhibitor properties that are important for that application. And the crest of this reports is the development of flow chart. So it walks the user to a process of various considerations and select the best inhibitor. It's a very nice flow chart. In fact, Trevor Place put this one forward. All these things are important, but more important is the quality control and quality assurance in the laboratory evaluation, which is the first step in selecting corrosion inhibitor. And the precision, establishment of the precision is important, and that is being emphasized in the section 9 of the reports. And obviously, field logistic considerations, how to evaluate, how to monitor inhibitor that has been selected. When we did the interviews, different companies had different observations or different considerations. Sometimes that will work only for them. Sometimes it may work across the industry. So that has been captured in section 12 of the report. Finally, efficacy. Efficacy, as the motion points out, there are four things: transportability, efficiency, secondary independent properties, and logistics. How to consider efficacy? Efficiency is one, but efficacy is more important. That is being emphasized in section 13, obviously definitions and so on. So we have 23 reports for each one of the applications. That is phase 2. When we did the phase 2, we also found that we have to categorize the inhibitor performance testing into 4 categories: screening test, selection test, special test, and secondary inhibitor properties test. Screening tests are within the scope of standardization in phase 3. That is typically carried out for a shorter duration under standard conditions. That is being used by chemical suppliers and owners as well as operators as an economic means for developing a short list of chemicals from several chemical suppliers. So this gives a level playing framework to select inhibitor from different chemical suppliers. This can also be used by owner operators to ensure quality of chemicals at various frequencies during routine operation. So that is a selection test. And we are in Canada, actually I'm in Canada, and we say that no two snowflakes are identical. Similarly, every pipeline operation is different, for which we have to carry out the test for a given field condition. Those tests, we call them as selection tests. And these selection tests are not within the scope of phase 3 because they are being carried out for a particular field operating conditions. We cannot standardize them. So these long-term selection tests are used by owner operators to select a chemical or a few chemical for a given field operating conditions, which cannot be standardized. That's why it is not within the scope of phase 3. Normally, when you say efficiency testing, we talk about efficiency with respect to general corrosion rate or pitting corrosion rate. However, we have to also consider the efficiency in terms of controlling special corrosion mechanisms such as under deposit corrosion or top of the line corrosion. So these tests, we call them as special tests. So we have identified some special tests to evaluate inhibitor performance to control under deposit corrosion and top of the line corrosion. They also fall under screening test category. And of course, secondary inhibitor properties, we have identified certain properties that need to be standardized. So in terms of deliverable, we'll go through these things in future webinars. We have identified 8 methodologies that needs to be standardized. 4 are on inhibitor efficiency, 1 on partitioning coefficient, that is how the inhibitor get partitioned from oil phase to the water phase. This is typically more important for oil transmission pipelines. We have identified inverted rotating disc electrode. We talk about inhibitor film thickness and film persistency. The film thickness was established at 3 microns almost in 1940s. So we want to quantify it using electrochemical quartz crystal microbalance. We'll talk more about it in future webinars. And we have to also establish a standard test method for under deposit corrosion, bisel or something else. And we also have to establish a standard test method for top of the line corrosion. That could be modified bubble test or UQCM. That is the deliverable of this phase 3. In terms of actual deliverable, we will have a step-by-step procedure to carry out the test for all the laboratory methodologies standardized in phase 3. When we develop new methodologies, we will also develop blueprints so that the sponsors can manufacture their own apparatus. One thing we found for the last 30 years is that unless you standardize the solution and the gas composition as well as procedures, you cannot develop a precision statement. So for which we identified, at least we need to standardize 5 solutions and procedures to prepare them so that the repeatability and reproducibility or the precision will be good. For all the 8 methodologies, we will establish the precision based on repeatability. When I say repeatability, is one person carrying out the experiments. And then at the end of the project, after the sponsors approve it, we will submit it to ASTM or AMP to develop standard test methods based on the repeatability statement. Within ASTM, they have got a 5-year time around. ASTM can publish a standard test method with the repeatability statement, provided the reproducibility statement can be developed within 5 years. So we are going to follow that route. So we will still be active within ASTM or AMP in coordinating those inter-laboratory studies that will be carried out after the phase 3 completion. So instead of sponsorship, the current sponsors of phase 1 and 2, most of them have joined in phase 3. They pay $20,000. New sponsors, if you are going to join for all 3 phases, it will be $50,000. If you want to join only for phase 3, it will be $25,000. And we also have a special category for third-party laboratories. They pay only $25,000, provided they commit to the development of precision statement after the completion of the JAP. If you look at the math, each sponsor will contribute to less than 5% of the total JAP cost.